everyone. Now we continue our class with chapter 6, frequency domain analysis. Okay, this chapter focus on word plot, and it consists of 7 material. First, it is introduction. Second, it is frequency response definition, word plot definition, frequency response plot. Five, it is a viewpoint of analyzing control system behavior. 6, it is logarithmic coordinate. 7, this is word plot construction. Frequency domain definition. What is a frequency response of a system? The frequency response of a system is defined as the steady state response of the system to a sinusoidal input signal. The sinusoidal is a unique input signal, and the resulting output signal for a linear system as well as signal throughout the system is sinusoidal in the steady state. And word plot definition. What is word plot? Word plot is a semi-log plot of the transfer function magnitude and phase angle as a function of frequency. That is what we say word plot. And frequency response, it is we plot in the polar plot. This polar plot is consists of horizontal axis. It is for real function because of this frequency response, and then the variable is function of frequency, and then the vertical axis is the imaginary axis. It is right as x. It is function of omega. Frequency response. This transfer function can be separated into magnitude and phase angle information. If the J omega, it is a transfer function, and it can be write as absolute S J omega angle theta J omega. And then if the S J omega same as Z J omega and log Z, it is we can see in the right side. It is for log Z J omega. It is function of log omega. It is for magnitude, and that is for phase angle. It is from 0 into minus 90. It is the phase angle. And if we drew the magnitude and phase angle using the software, it is like this. It is the software result. Okay, viewpoint of analyzing control system behavior. This we can do using Rutherford criteria, where S is equal to tau plus J omega. We have done subtropius. Root locus is S equal to tau plus J omega, and also we have initiate both diagram of plot is equal to J omega. Now we study about it. Nyquist plot, it is just S equal to J omega. It is not consistent our subject. Nichols plot also not consistent of in this course. And time domain analysis we have done previous. Okay, this linear time invariant system with the input is the sinusoidal RT equal to A sin omega t. A, that is the magnitude. And then they add output also in kind of sinus yt equal to B sin omega t plus C, where the magnitude is B per A, it is the derivative of magnitude, and then phase angle it is C. This block it is the simple closed loop system. It is steady state response where the transfer function is ys per rs is equal to ds divided with 1 plus GSSS, and then S equal to 2 plus J omega. It is we transfer into S J omega because of we analyze it in frequency domain, and the magnitude of this transfer function is the magnitude it is absolute J omega divided with one absolute 1 plus J omega is J omega, and then it phase angle is equal to the phase angle of J omega divided with the phase angle of plus 1 plus J omega is J omega. Okay, this is the magnitude and phase angle. Okay, logarithmic coordinate. This into kind of in decade it is dex equal to log 10 omega 2 per omega I, and then for octave it is equal to log 2 omega 2 per omega 1, and from this figure we saw that the gain magnitude is many times expressed in term of decimal or dB. dB is equal to 20 log 10 A, where A is the amplitude or gain. A decode is defined as a 10 to 1 frequency range. It is 10 to 1 frequency range. While n octave is n2 to 1 frequency range. It is in 20 dB per decade. It is equal to 6 dB per octave. It is the relationship between decade and octave. Okay, word plot construction. It is, for example, this is the general form of transfer function ys per rs, and then there are four things that we should consider here. First, it is k and z plus s plus z. Sorry, is the 0 and s plus p, and for full, and also as plus b. This the our constant is for constant or for cases from this general transfer function. Okay, we look at one by one. First, this case for case 1 is for k. Okay, this the magnitude it is absolute k in dB. It is equal to 20 log absolute k dB, and then if you see it is the plot constant value because of k it is constant value, and then for phase angle there are two constraints, and the phase angle of k is equal to 0 degree for k more than 0. It is the plot, and then 100 degree for k less than 0. It is the plot. Okay, it is for if constant, if the constant part of the transfer function. And then next is case 2. It is 1 per s power p. Okay, the magnitude is because of s we in this frequency domain we change into j omega, and then the magnitude it is become absolute 1 per j omega power p. Okay, it is equal to minus 20 p log omega dB. Why minus? Because the SCDC in the denominator part. Okay, if we see it is for p equal to 2, it is the plot of the magnitude, and if we p equal to 1, it is the plot. Okay, and then for phase angle, this the phase angle 1 for j omega power p, it is equal to minus 90 multiple p. It is for p1, it means 90 degrees, minus 90 degrees, and for p equal to 2 minus 180 degrees. Okay, etc. Okay, for case 3, it is s power p. It is the magnitude. It is absolute j omega power p. It is equal to 20 p log omega. If we see here, that is the plot. This plot it is for p equal to 1. This is plot for p equal to 2. Okay, and now for phase angle, the angle of j omega power p is equal to 90 degrees multiple p. Opposite with the frequency. P it is for p equal to 1, it means 90, p equal to 2, 180 degrees. Okay, then the case 4. Case 4 in a per s power s plus a, or 1 per a s plus 1 power minus 1. Okay, the magnitude is absolute 1 plus j omega per a power minus 1 equal to minus 20 log square root 1 plus omega per a square. This the absolute this. Okay, it means equal to minus log 1 plus omega per a square. And then in this case, if the omega less than a, then omega per a is 0, then dB it is minus log 10 log 1, it is equal to 0 degrees. This part. And then for omega more than a, it means 1 plus j omega per a is approximate this omega per a, and the dB it is the amplitude is minus 20 log omega per A. This is the result. This is the plot. And then derive this, we can also write minus in the bracket 20 log omega minus 20 log A. This is the mechanism how to plot this. And if omega equal to A, it means 1 plus J 1. The dB it is equal to minus 10 log 2. It is equal to minus 3.01. Minus 3.01. If omega equal to A. If omega equal to A. Okay, if A equal to 1, this is the result. Then this for phase angle. Phase angle of the 1 plus J omega per A, it is equal to 0 minus tangent inverse omega per A. If omega is less than A, omega per A approximate 0, and the angle of GH it is equal to tangent inverse 0, and then 0 degrees. This 0 degrees. And then if the omega more than A, omega per A it is approximate infinite, and then the angle it is minus tangent inverse infinite. It is equal to minus 90 degree. It is the minus 90 degree. It is minus the 90 degree. And this part is for A equal to omega equal to A. It means the tangent inverse minus 1. Tangent inverse 1. Tangent inverse 1. It is tangent inverse minus 1. Tangent inverse minus 1. It means there is minus 45 degree. It is minus 45 degree. It is tangent inverse. It is minus tangent inverse 1. Minus tangent inverse 1. This it means minus 45 degree. This is the mechanism. This first for omega less than A, omega equal to A, omega more than A. It is for omega less than A. It is for omega equal to A, and it is for omega for omega more than A. Okay, case 5, where S plus A per A, or 1 per A plus 1 per AS plus 1. Okay. The magnitude is absolute 1 plus J omega per A equal to 20 log square root 1 plus omega per A square equal to 10 log 1 plus omega per A square, because of if the square root it is it means power half, and then if we eliminate it become and then we change into here, it means 20 multiple L half, and then we get 10. This is the why here it is 10. And then for omega less than a, there is omega per a, it is approximately 0. dB equal to 10 log 1, it is equal to 0. Okay, and then for omega more than a, it means 1 plus j omega per a, the approximate omega per a, it is the dB, it is 20 log omega per a. Okay, and equal to dB 20 log omega minus 20 log a. This is the graph. It is for omega more than a. Okay, if the omega equal to a, and then we get that 1 plus j omega. 1 plus j omega equal to dB, it is 10 log 2, it is 3.01. 3.01. It is for omega equal to a. Okay, and then for phase single 1 plus j omega per a, it is equal to tangent inverse omega per a. And then for omega less than a, omega per a approximate 0, and then the angle, it is tangent inverse 0, it is at 0 degree. It is 0 degree. And then for omega equal to a, it is j plus 1 plus j 1. The dB, it is log the angle, it is the angle of gs, it is tangent inverse 1, it is 45 degrees. And then for omega more than a, it is omega per a approximate infinity, and then the angle of gs, it is tangent inverse infinity equal to 90 degree. It is 90 degree. This is the result. 90 degree. Okay, this is case 5. And if we try to plot using software, for example MATLAB, there is the result. It is, if we approximate, it means we do it manually. There is for manually, and there is for actually using software. And also there is the hardline, is for approximate, and there is for actual using software. Okay, it is case 6. 6, it is Ts equal to omega n square per s square plus 2c omega n s plus omega n square. This is the prototype of second order system. And then if s we change with j omega, then we got this t j omega equal to omega n square divided with in the bracket omega n square minus omega square plus 2 J C omega n omega. Okay, and then we also can write like this: Tj omega equal to 1 per in the bracket 1 minus omega per omega n square plus J 2C omega per omega n. Okay, it is for the angle, this angle of the J omega, it is equal to minus tangent inverse to C omega or omega n divided with omega n square minus omega square, or equal to minus tangent inverse to C multiple omega per omega n divided with 1 minus omega in the bracket omega per omega n square. Okay. And then the amplitude for omega per omega n less than 1, it is 0. And then for omega per omega n equal to 1, the amplitude is minus 20 log the bracket to C. And then if omega per omega n more than 1, the amplitude is minus 40 log omega per omega n, while the angle of function J omega for omega per omega n less than 1, it is 0 degree. Omega per omega n equal to 1 minus 90 degree, and then omega per omega n more than 1, it is minus 180 degrees. It is the plot of magnitude and phase. It is the effect of damping ratio. You see here, if the damping ratio highest, the amplitude is reducing. Although we see the phase angle will reduce by increasing the damping ratio. This is the effect of damping ratio into the magnitude and phase angle. Example, if we have transfunction Ts equal to 50 in the bracket S plus 2 divided with S in the bracket S plus 10, and then we can change this transfunction become Ts equal to 10 in the bracket 1 per S multiple in the bracket S plus 2 per 2 and then multiple in the bracket S 10 divided with S plus 10 cross bracket. Okay, like this. Okay, we look at how the solution is. Okay, with this, if we try to answer it with manual, it is amplitude for this one, it is for 1 per S, this, and then it is for S plus 2 per 2, and there is it is 10 per S plus 10, this part, and there is for 10, it is for 10. Okay, like it means equal to K, and then if the last part we see here, it is here, and then here it is the last um, magnitude. And then for phase angle, we see here is for 10 is 0, and there is for here it is s plus s plus 2 per 2, and there is this, it is 10 per s plus 10, and it is for 1 per s, and then at the end the last construction is we get, and there is this plot. This if we plot using software in the actual, and there is approximation. If we it mean we if we uh, make the graph, it is manually, it is the approximation. Okay, minimum phase system. If the it is the um, general form transfer function. Here it is the again it is this part, it is for 0, and then it is the integrator is power n, it is the number of integrator, s plus p, it is for full, where z more than 0 and p more than 0. It means all the 0 it is more than 0, and then all full it is more than 0. And then if type 0 system, it means n it is equal to 0, and as the if and then we will get like this, ts equal to kp p1 and divided with s plus p1, and then this the magnitude, it is the magnitude for the transfer function g has db 0 until p1, and then this will be down here. It is 20 log kp equal to a. Okay, this for 0 dB per decade. Okay, type 1 system, it means n equal to 1. This is the system. Ts equal to kp p per s, the bracket s plus 1, and for 20 log kv, it is again equal to a. It is a, it is a, and then 20 log kv per j omega 0, it is equal 0 dB. It is the graph, and then it is for omega equal to kv. Okay, it is will be down 40 dB per decade, and it is this line, it is minus 20 dB per decade. Okay. Next, for type 2 system, mean n equal to 2, this here we see the transfer function, and if 20 log ka, okay, it is the again equal to a, it is a, and then 20 log k a per j omega 0 square, is equal to 2 dB, 0 dB, it is for 0 dB, where it is omega 0 square equal to ka. It is the we get the condition, it is 0.1 p, this in this part, it is p, in this 10p, it means the omega equal to 10p. This is the graph. From here, they are decrease minus 20 dB, minus 60 dB per decade. Okay, relative stability. A transfer function is called minimum phase when all the pole and zero are left hand plane, and non-minimum phase when they are right hand plane pole or zeros. The minimum phase system, it is stable. The gain margin is the distance on the both magnitude plot from the amplitude at the phase crossover frequency up to the zero dB point. GM, it is the gain margin, it is minus dB of GS measured at the phase crossover frequency. This we call gain margin. Then the phase margin is the distance from minus 180 degrees up to the phase at the gain crossover frequency. It means PM that is equal to 180 plus phase of GH measured at the gain crossover frequency. It is the definition of gain margin and phase margin. Okay, open loop transfer function, it is GH per SS. Closed loop transfer function, it is 1 plus GSSS. The open loop, this is CE characteristic equation. Open loop stability, there is pool of GSSS in left hand plane. This closed loop stability, it is full of GSSS in left side of minus 1.0. It is the different open loop. It is in left hand plane, the left hand. But for closed loop, it is you see here minus 1.0. That is the different. If there is the imaginary axis for open loop stability, it must in here. But for the closed loop, it is from minus 1.0. It is stable. Okay, it is in the plot, and in the plot, the system it is for amplitudes plot. It is gain crossover frequency. It is omega G. It is the gain crossover frequency, and then YP. It is the gain crossover phase crossover frequency. It is YP. Okay. This is if the system stable. This is the position. The stability is in the right, in the left side. The this the angle 180 degrees, 90 degrees, minus head minus 90 degrees, minus 180 degrees. It is the plot. It is YP, the crossover, and there is the crossover. As you see here, but here it is 0, and then change again. It means decreasing. Okay. It is for unstable system. unstable system. This is the right side. Explain. Side is the unstable system. You can see the look like of magnitude plot, and you can also see differentiate with the previous the phase angle. It is the unstable. This is the unstable part. Okay, for diagram, this magnitude phase angle and magnitude. It is the magnitude and it is the phase angle. It is for stable. It is for unstable. Okay, both plot summary. Straight line approximation of the both plot may be drawn quickly from knowing their poles and zero. This response approximate a minimum near zero, and then the response approach a maximum near pole. Then the overall effect of constant zeros and pole in the plot, it is this we look at in table. Term it is constant k. The magnitude breaks it is in A. Asymptotic magnitude slope is 0, and asymptotic phase shift it is 0 degree. And then for 0, it is magnitude breaks it is upward, and then asymptotic magnitude slope is plus 20 dB per decade. And then the asymptotic phase shift it is plus 90 degree. And then for full downward, asymptotic magnitude slope is minus 20 degree per decade, and asymptotic phase shift is minus 90 degrees. And express the transfer function in the standard form. This is in standard form, and as we have changed with j omega, there are for different vector constant gain k term, this, and then pole or 0 at the origin, and then pole or 0 of from 1 plus j omega 2, and then quadratic pole or 0 of the form 1 plus 2c j omega 2 plus j omega 2 square. This is the four different vector. We can combine the constant gain term k and n pole s or zeros at the origin such that the magnitude cross 0 dB at the pole CDD pole is k per j omega power n, and then omega 0 dB is equal to k power 1 per n. It is for pole. Then for 0, k j omega n, it is omega dB, it is equal to 1 per k power n per n. Define the break frequency to be at omega equal to 1 per 2 with magnitude at plus minus 3 dB and phase at plus minus 45 degrees. And then there is the summarize of the plot in the table. You see it is the vector and it is the magnitude behavior for low frequency break and asymptotic, and also there is for phase angle behavior for low frequency break and asymptotic constant. This is for low frequency break and asymptotic it is the same 20 log 10k for all frequency, and then for phase behavior it is 0 degrees for all frequencies. For full or zeros and origin it is the magnitude plus minus 20 n dB per decade for all frequency with crossover of 0 dB at omega equal to 1. The phase angle it is plus minus 90 degree multiple n for all frequency. First order atau simple full for 0. It is for low frequency 0 dB. For breaks it is plus minus 3 n dB per dB at omega equal to 1 per 2. And then asymptotic it is plus minus 20 n dB per decade. It is low frequency it is phase it is 0 degree. For break it is plus minus 45 n with slope plus minus 45 degrees multiple n per decade. And asymptotic it is plus minus 90 degree multiple n. Then quadratic full for 0 dB for low frequency, and then break it is C at damping ratio at omega equal to 1 per 2. We should constant at the damping ratio. Asymptotic it is plus minus 40 n dB per decade. For phase angle it is 0 degree for low frequency plus minus 90 degree multiple n for breaks, and asymptotic it is plus minus 180 degree for multiple n for asymptotic. Single full N0 bot plot. This for single full N0 bot plot. We see here if the full at omega p equal to 1 per 2. You see here there is the gain, this yp, and there is the phase angle. The yp is where the gain change. Here you see here it is it at the angle it is the phase angle 45 minus 45 degrees, and assume k it is equal to 1, mean 20 log 10 k it is equal to 0 dB, and this part it is 0 at omega z equal to 1 per 2. This in the right side the surface it is for full it is for 0. See here this the gain at omega z at omega z the big over the gain it will increase. Also you see here this the difference between full at 1 per 2 or and 0 at 1 per 2. About plot refinement. The refinement of the magnitude characteristic for first order full N0 is possible since magnitude at half break frequency absolute has one f l half has absolute has in the bracket has function 1 per 2 omega b. It is equal to plus minus 1 dB. Magnitude at break frequency is absolute has omega b equal to plus minus 3 dB. And then magnitude at twice break frequency is absolute 2 has absolute has function 2 omega b equal to plus minus 7 dB. Second order full or zeros require the damping ratio values be taken into account. Okay, we plot to transfer function. We can also take the word plot and extract the transfer function from it. Also, in really there will be error associated with our extracting information from the graph. First, determine the constant gain factor K. Next, move from lowest to the highest frequency, noting the appearance and order of the pool and zero. Frequency response plot, bot plot, a real plot, graph construction. And this asymptotic curve for j omega 2 plus 1 power minus 1. It is if we see here before 1 per 2 omega equal to 1 per 2 it is 0 and then after that they will decrease by 20 logs g dB. Okay, this frequency response plot bot plot real pool. It is bot diagram for j omega power plus minus n. Is here is the effect of the power, and also there is the phase angle. This is the effect of integrator, number of integrator. Okay, this frequency response bot plot real pool. It is for bot plot a diagram for in the bracket 1 plus j omega 2 close bracket power minus 1 here at the crossover when the crossover, and again and phase margin. Let's say that we have the following system where k is a variable constant, gain and gs is the plan under construction. This is the block diagram. K is gain and then gs is the plan. The gain margin is defined as the change in the open loop gain required to make the system unstable. The system with greater gain margin can withstand greater change in system parameter before becoming unstable in a closed loop. Keep in mind that unity gain in magnitude is equal to a gain of 0 dB. The phase margin is defined as the change in open loop phase shift required to make a closed loop system unstable. This phase margin and gain margin. The phase margin is the difference in phase between the phase curve and minus 180 degree at the point corresponding to the frequency that give us a gain of 0 dB. the gain crossover frequency is omega GC. Likewise, the gain margin is the difference between the magnitude curve and 0 dB at the point corresponding to the frequency that gives us a phase of 180 degrees is the phase crossover frequency omega VC. This the plot how to show the previous definition and the gain and phase margin. There is, you see here, is the omega GC, and there is the omega VC. It is for gain margin, and there is for phase margin. Okay, this is example of bot plot. It is for a system. This is transfer function, and if you use MATLAB form, if you use MATLAB form, there is the code. After you run the code, you will get this. It is for gain margin and it is for phase margin. This is continuous. This magnitude and the phase margin. This is another example. Here there is the